So here is the instruction, the tutorial, and the first thing it says is to make sure that the parameters, constraints, and relations are visible, and then it will start creating the parameters needed for a gear. So I'll get started on that, and I put this on the monitor on my left side, so you're not going to see that, but I can see it and follow, and it accelerates my work. So here we go. We start a new part, and it says give it whatever name you want. So Spur gear doesn't matter in this case. Just we go to tools and options, and then we make sure that those parameters and relations are visible. So we click on infrastructure and then part infrastructure, and then under display we make sure all of these guys are checked. For my case they are, so if not, make sure they are checked, and then we start creating the parameters. The first parameter you need to create is the number of teeth on the gear, which here it says is an integer number n, and set it to 32. So first here we make sure we are in the part design environment, and we click on fx from the knowledge toolbar, and new parameter of type, we choose it to be integer, and we say basically the name of this, I want it to be n and the value of it to be 32, and I say create that. Now it gives it a new name, so let me just change it here at 32. So that is the first parameter. The next parameter that you need in a gear is called diametric or diametral pitch, P. Okay, and the meaning of diametral pitch is, so here these are two gears that are meshed together and work together, and as I said, the meaning of diametral pitch, which is 1 over the gear modulus, so diametral pitch P is basically the number of teeth in the gear n divided by the diameter of this imaginary circle, which we call the pit circle. The pit circle is an imaginary circle where two gears are working together. Their pit circles, as you can see, this one and this one, are tangents to each other. Okay, so pit circles are imaginary circles that are tangent to each other when two gears are meshed, and the contact point is always on the pit circle. So diameter of that pit circle in the denominator, the number of teeth on the numerator, this ratio we call it diametral pitch, or P. Okay, so if I know n and if I know P, then from here you can find, of course, what? The diameter of the pit circle, which is n over P. Okay, so we are defining n and P, and then from there we can find D. So here it says call that P, it is a real value, and set it to 8. So this is 32, that is 8. If you divide, the diameter of the gear is going to be 4 inches. Okay, the unit for P is the number of teeth per inch. It's 1 over inch, or yeah, because n actually is just a number, it doesn't have units. So the unit of diametral pitch is 1 over inch. So here 32 divided by 8, you get 4 inches. So let's go back. Now I want a real number, and say create that, and then I call it cap P, and I make sure this guy is 8. So I added that. The other parameter that is important in a gear is called pressure angle. And what is pressure angle? So when you have two gears where the teeth profiles are touching each other, okay, so this involute curve and that involute curve here, if I zoom in, So in this area where the two profiles are touching each other, let me draw that for you. Okay. So in this area, if you draw the tangent to both surfaces, it's going to look like that. And then the common normal is going to be this black line here, this guy. This line here is where the force is exchanged, because when you have contact, the normal forces are perpendicular to the common tangent. So the force that is exchanged between the two gears is along this line, which we call pressure line, and then the angle between this pressure line, or we call it line of action, the angle between that and then this horizontal line here, which is perpendicular to the line that is connecting the centers together. Okay, so this vertical line connects the center. If you draw a perpendicular to that at the contact or midpoint here, not midpoint, I mean the point that the two pitch circles are tangent. If you draw a normal to that center to center, which is this horizontal line here, and if you draw a line of action, the angle between them is this guy, we call it pressure angle. Okay, so one component of that force, so if the force exchange between the two gears, if I call this F, so F is the force exchange between the gear teeth, and I call this guy to be phi, then you can see that one component of F is gonna pressure the two gears against their bearings, and the other component of this force is gonna create what? Is gonna create a moment about the centers and make the gears rotate, right? So this guy is F cosine phi, and this one is F sine phi. Clearly, the smaller the phi is, the bigger the component of the force that creates torque, and the smaller the one that pushes the gears against their bearings. Okay, so just wanted you to know about the meaning of pressure angle. So it says the pressure angle, you make sure the unit is degree and call it phi. So here we go with angle, and we create one and then call it phi, and the value for that you set it to be 20. There we go. And one other thing that we have is the base circle. So in general, in a gear, there are 4 circles. There are 4 circles in a gear, 4 major circles. What are these? So if you look at this gear, there are, as I said, 4 circles. One is this imaginary one, as I said, that passes through the contact point. We call it the pitch circle. The other one is the one that is passing through the tip of the teeth, right? So if you draw a circle that is passing through the top of the teeth, this guy, this is another circle. There is one that is passing through the roots of the circle, so there is a root circle, or we call it Addendum circle, this guy. And then this one that is passing through the tip of the teeth, we call it the Addendum circle. Okay, so Addendum, Addendum, and then there is a 4th circle, which is actually somewhere between Addendum and pitch, so that's here, and that is where the involute profile starts. So each one of these profiles of the teeth, this side and this side, both of these profiles are, as I said, a curve called involute, and I'm going to show you. But not all of the tooth profile is involute. Only the part of it that is above this circle is involute. The part that is below the circle from between this circle and the dedendum, this part is not necessarily involute. It doesn't need to be, because there is never going to be any contacts down here. Never the point of contact or any point of one teeth would touch any point of the other teeth below the circle. And this circle has also a name. We call it the base circle. Let's see. Yes, you can see it here. Okay, so that is our fourth circle. We call it the base circle. Now, you can show that the diameter of this base circle is diameter of the pit circle, and then times cosine of the pressure angle. Okay, so if I know d and phi, which we define, I can also get my diameter of the base circle. So my next step will be, I'm going to implement now this formula and this one. So now that I define my three major parameters, phi, n, and p. So the major parameters in a gear are these three guys. Once I know them, I can determine everything else. And that's what I'm doing. Now I'm going to put these two formulas in. So here we go. So the first thing it says is PD, the pitch diameter, PD. And it says make sure that is a real number, also the base circle. So we make sure they are real and create one, and then we would call it PD, pitch diameter. Here we just call it D, but here we're going to call it PD. And this PD, of course, we have to calculate this PD, okay? We don't enter a number for it. So we add a formula for PD and say PD is what? As you saw in this formula, it is n over p. So all we need to do is to say n divided by p. And you see it is 4 inches. And it is totally fine. Now here I did define it as a number, although it is in inches. So I would like to change that and change it back to length, because this is just a real number. So let me get rid of this and redo it, if you don't mind. But I say I want it of type length, and then create one. I would call it PD, and then I would add a formula and say this is n divided by p. Okay, but now you know this n divided by p is just an integer number divided by a real number. It's not going to be of type length. So if I multiply 1 inch times that, it should convert it into inches for me. Now here my default unit is mil, but this is actually 4 inches. So if you want, before I go any forward, I go to my options and make sure my units are in inches, because here they are in mil. That's why it is converting it back to mil. So I go back here, and now you see it's 4 inches. Good. Then I create another parameter of type length, and that is going to be BD. And this BD, which is base diameter, I'm going to again add a formula for it, and that is going to be PD times cosine of phi. And in CATIA, cosine and sine accept their argument in degrees, not in radians. And PD is already in inches, so this guy is also going to be in inches, hopefully. Phi cannot be used. You want to go back to the editor. So we have to make sure that we do our job right. Let's make sure we have phi. I don't see phi here. 1 second. Let's see. Integer 132. What is integer 1? 32 divided by n. Okay. What is this? That was n. We have p, and then we have angle 1. Okay, that's y. It's all messed up. So we have n, p, phi, pd. We don't need that. 32 divided by n. What are these? Oh, okay. BD. Okay, let's go back and say this is PD times cosine of phi. Now I have phi. It should take it from me. There we go. So now I got this one. And now we have to create the diameter of the addendum and didendum circle. The diameter of the addendum circle, the big circle, the outer circle, is the diameter of the pitch circle plus 2 inches divided by p, okay? So there is a formula for that. So now I'm going to create a new parameter of type length, and just need to make sure everything is set. And this length 3, I would call it OD, the outer diameter or addendum diameter. And this guy, we add a formula for it. It is going to be pitch diameter plus 2 inches divided by p. Okay, so I got that one, and finally I get one more, and this is going to be the root diameter, we call it, or the didendum diameter. And this root diameter, it is going to be the pitch circle minus 2.5 inch divided by p. Okay, and there we go. So again, I write them for you. So if I want to organize here the parameters that I need to define are p, n, and phi. Then the formulas that we have to use is the pitch diameter is n divided by p. The base diameter is pitch diameter times cosine of phi. Then the addendum diameter or outer diameter is pitch diameter minus 2 divided by p. And the root diameter is pitch diameter minus, this is plus, sorry, this is minus 2.5 divided by p. Okay, so these are the 4 formulas for the diameter of the 4 circles. I mentioned that these are important in any gear, the 4 major circles. Okay, so we have created all of them. The other thing we need is a parameter called clearance. Again, that is a real number. We call it CL, and clearance is 0.25 inches divided by P. Okay, so the 5th one is a parameter called clearance. And okay, my pen doesn't work for some reason. Let's see. I don't know why, but it doesn't. So clearance is 0.25 divided by P. Okay, and what is clearance? Clearance, as I mentioned, is, as I said, not all of the profile is involute, only the portion of it between the outer diameter and this base circle is involute. The part between the base and what? And the root circle, this portion, that guy here, this part is not involute, and that is the part that the two gear profiles will never touch each other in that area. Okay, so in this area, the two teeth profile will never touch each other. And that is according to this formula. Good. So far, I guess I have created the parameters and formulas I needed, and I should be able to see them on the tree. Now, I also need some functions. These functions are used to define the involute curve. Okay, so the involute curve is a complicated curve. It's a parametric curve, and the equation of that is nothing similar to a circle, an ellipse, an SP line, or anything like that. Okay, so the formulas for a involute curve, if you draw it in the YZ plane, is y equal to, or y of t, as I said, is parametric. Y of t is equal to radius of the base, which is here diameter of the base, divided by 2, correct? Times what? Sine of t, and then minus t times cosine of t, and then z at t is equal to the same number, radius of the base circle, and this is going to be cosine of t, and then plus t times sine of t. Okay, so this is for the involute curve, y and z, these coordinates of every point on that curve, right? So if this is an involute curve, such bad. Okay, so if you plug in t of 0, you're going to get 0. If you plug in t of 0, you're going to get 1. So if this is z versus y, if you plug in t of 0, your y is 0, your z is going to be bd over 2, and then it keeps going like that. Okay, and so here is t equal 0, and here t keeps increasing. This curve is the involute curve. These are the equations for it. And there is a lot of proof behind why we should use an involute curve in gears. As I said, the main reason we use involute curves is unless the profiles of the teeth are involute, the important thing in gears, which we call a speed ratio, is not going to be constant. What is a speed ratio? So speed ratio in gears is defined as the RPM of the input gear divided by the RPM of the output gear. and this guy should be constant. So when the input gear, so let's say here the bottom one is the input and the top one is the output. So when the input rotates with the constant RPM, if the ratio is constant, it means also what? The output rotates with the constant RPM, and that's what you want, right? If these gears are used in the gearbox in your car transmission, and the input gear is coming from the engine and the output gear is connected to your tires, of course, you want to make sure that when you are not changing the RPM of the engine, which means you are not pushing on the accelerator or pushing on the brake, the RPM that goes from the transmission out to the tires does not change, which means your tires also what? Rotate at a constant RPM, or in other words, the speed of the car is constant. You don't want to keep the accelerator of the car in the same position, no brake, nothing. You want basically to cruise, and then you look at the RPM of your car or the speed of your car, and the speed goes 50 miles an hour, 60 miles an hour, 20 miles an hour, 40, 20, 30, 0, 5, 10, and so on, right? You don't want your speed of the car oscillates when you have not pushed the accelerator or you didn't push the brake. So only this constant speed ratio is feasible if the profile of the teeth are involute. If it's not involute, then you will not get the constant speed ratio, you get a variable speed ratio, which is really horrible. Okay, so there is a ton of proof. You need to take a machine design or a mechanism design and analysis course to know about that. But just want you to know that this guy is constant, and if they are involute, you can easily show that this is going to be the diameter, PD, the pitch diameter of the output gear divided by pitch diameter of the input gear. And since these two diameters, pitch diameters of these two gears are constant, the ratio of them is going to be constant. Okay, so just some background info for you so that you digest this gear a little bit better. So now we're going to go to the YZ plane, go to sketch, and before we can do anything, we want to add these two functions now and be able to evaluate these functions when t goes from one number to another so that we can get those involute curves. So first we need to create functions. Now functions are different from formulas or parameters. And where can you create a function that you can evaluate at some point? So they are in this knowledge toolbar, but they are not fx. You have to expand the design table, and that's this guy, FOG. It's called the law. So law is the same as a function. So I want to create a law. Then basically it says create a law, call it Y, and then okay that. And now it says, okay, what parameters are involved in law? So we have a t and a y, correct? There is a t and a y. T is a real number, y is a length. So it says create for me a new parameter of type real, right? And then if you basically go here, you can change the name. So I want it to be t. Then create one of type length for me. And then the name of that, you call it what? Y. So I got both of my parameters, and here you can type the function that you want between y and t, which was y was bd divided by 2, and it recognizes bd because it is a parameter we define, and then times sine of t minus t cosine of t. The only problem is t is a number, and when you say sine or cosine, they need an angle. So in order to convert t, which is a real number, into an angle, we have to basically multiply them by something to turn them into angle, and here we use 1 radian. So we multiply t by 1 radian to convert them into an angle, and that should create my function. Yes, so it is created. It didn't pick on me, so that's this function. It is written down below the formulas. Okay, that's y as a t, and whenever I pass a t to it, I can evaluate y at some t value. I'll show you. Then we repeat the same procedure for z. So we go here, we call it z, we go inside, new parameter, real, call it t, and then get another one of type length, call it z, and then here we type our function again. Z is bd divided by 2 times, and then here you have cosine of t minus or plus t times sine of t, and t, as I said, we multiply by 1 radian in order to calculate its sine and cosine. There we go. These are the 2 functions. Okay. Now, there is one more parameter that we have to create. It is the tangent of phi, the tangent of the pressure angle. We need that later, as the involute curve intersects the pit circle when t is tangent of phi. Okay, so if you go here, you see the involute curve, right? It intersects the pit circle here, here. This is where t is equal to tangent of phi, and if I remember correctly, when we started down here, that is where t is equal to 0. Okay, so we need that, and we call it tp. So we define a new parameter, tp, which is just tangent of the pressure angle, and it is gonna be of basically type real, because it's tangent of an angle. So I go here, I create a parameter of type real, I call it TP, and the formula for it is going to be tangent of phi. Okay. There is one more parameter that this tutorial suggests we do, and that is a shift angle, theta r, which just help us to center the top tooth about the z-axis. So what do I mean by that? So if you look here, if this axis up here, this one that goes up, we call it z-axis, and then this one that goes horizontally, we call it y-axis. Let me just draw something for you here. So this one is the y-axis, and this guy that goes all the way to top, we call it the z-axis, okay? Then if you look at this tooth here, this one, this tooth is centered around the z-axis, right? This curve and that curve are centered about z-axis. Well, if we start the involute curve with the same way that I mentioned for you, the profile is actually going to start right on the z-axis, not with some offsets. So instead of, if this is z-axis and this is y, instead of your first teeth to look like that, symmetric about the z-axis, instead of that look like this, it would look like this actually. Okay, so here we try to create a shift angle, which is, if this is the center here, if we can find this angle theta r and shift our involute, instead of starting right on the z, started off center and started off z-axis, starting from here, then we can center our top tooth about the z-axis, and that makes later, when we want to do a circular pattern, it makes life a lot easier. So here we add one more shift angle, which we call it theta sub r, and the formula for it is tangent of phi minus phi and then plus pi over 2n. Okay, so the shift angle will do this one as well. And here, if you look, it has to end up, because this is a number, this is in degrees, and this is actually something like radians. So the important thing is you make sure when you type this formula in, it has a consistent set of units. You cannot add numbers, degrees, and radians all together. Okay, that is not going to be possible. Okay, so this number, you have to convert it into radians. So you multiply this number by 1 pi to convert it into radians. And then this guy, since it doesn't recognize pi just recognize it as a number. So the instructions suggest that we multiply this by 1 radian and multiply also this by 1 radian. Okay, and we assume that in here it can add degrees and radians together because phi was in degrees, it was 20. If it doesn't, then we also have to convert this degree into radians so everything can be added together. So here we add one parameter, it is of type angle, and we say get me that, and I call this theta sub r, and I create a formula for it, and then we say tangent of phi times 1 radian minus phi and then plus it says pi times 1 radian divided by 2 divided by n. So here we assume that CATIA understands pi. So when we type in pi, it knows that's 3.1415. Is this going to work? Let's find out. Yes, it did. And it converted it into degrees. So it could add degrees and radians into each other. It understood the keyword pi. It knows that pi is actually a variable and a parameter, and it understands it, CATIA. And it could add degrees and radians together and convert the total result back into degrees. So we need to shift it 3.67 degrees to the left to center it on about the z-axis. So now I got everything. I'll do a save before I lose anything. And I could call it Spur gear, okay, which is a simple gear, the simplest that you can use in real life. So you got everything now. And now you are on page, what page is this? Let's see, you are on page 9. So I went through almost half of it so far. And that is the most important thing. Now let me create the involute curve for you. Evaluate, connect them with spline, mirror it, trim it, and create one tooth profile. Once you create one tooth profile on page 14, the rest of it is nothing important, okay? So first, it asks you to put all of the points for the because what you do is you really are going to, for this involute curve, you are going to evaluate that function, those functions for y and z. You're going to evaluate them at a bunch of t points. So at some values of t, you evaluate them, you get a bunch of points, and then you use an spline and connect them together. Okay? And since you have a bunch of points here, when you go to CATIA, then on your tree, you're going to see a ton of points showing up on the left. And that makes your tree really big. So in order to keep everything in a folder, all of those points that I need for creating the involute curve, all of them under one single branch, one single folder, I insert something called a geometric set. And a geometric set is actually a folder that you can put non-homogeneous entities in the same folder. So you can store in it a point, a bunch of points, lines, surfaces, everything, okay? It's a folder of mixed things. So first we go under insert, okay? Let's get out of here first. And we insert a geometric set. Okay, and you have to give it some name. So here I call it geometric set 1, okay, or dot 1, as the instruction says, and then we take this way. Now here, for some reason, it called my part 32. I don't know where it got that. So part name is gear, not 32. It has nothing to do with 32. So I got this. This is, as I said, the folder, and inside this folder, I can create any number of points that I want. Okay. Now, it is also asking you to create an axis system, so that when you create the 3D points, because you're going to use this point command and creates a bunch of points using their 3D coordinates, it wants you to specify the location of those points with respect to a customized coordinate frame. I'm not sure if it's needed, but let's go step by step through the in tutorial. So we go under insert and we create an axis system. Okay. And yeah. We just need to make sure we set the origin right. And we set the axes right. So it says select the default location on the origin, the desired origin. Okay, so you can put it anywhere. Let me skip this. I'm not sure if we really need that. So what I will do is I'll go and start with my first point. Now for the first point, x is going to be 0, y and z will follow those formulas because we want to create the points on the yz plane, so their x is 0. So for y, instead of a number, I evaluate that function y of t at t of 0. Then I basically evaluate it at bigger values of t. Okay, so your instruction says evaluated at 0, TP over 4, TP over 2, 3 TP over 4, TP, and then 4 more values. So at 9 values, evaluate Y and Z. In other words, you create 9 points and then connect the 9 points together using spline to get your involute curve. So here, instead of me typing a number, I try to evaluate the Y function at some T. How do I use that? I use the command evaluate, or I can add a formula. So here, okay, I say for Y of this, I right click and say I want to create a formula, and says, okay, what is it? And I said relations \y dot evaluate at 0. So I say go under relations. There is a law, a function called y, and then what? This function has a method, has a, if you need here to know some programming, it's called a class, and this is called an basically a function or a method of the class. In other words, forget it. Evaluate that function y at t of 0. That's all it is. Okay, evaluate it at t of 0. So this is equal to y at t equals 0. That's all it is. Okay, and I got that. Then I do the same thing for z. So I can even double click on this guy here, and it brings that for me. Relations \z dot evaluate at 0, right? So that's all you need. Here is a little bit like coding. And there we go. So my first point is there, that y and that z. Yes. So I got this one. Now, I keep repeating, but this time I evaluated at other t values. So I click here again, and then I say edit formula, and then here I calculated at TP over 4. Remember, TP is an angle, or it is a value, not an angle, is where the intersection happens. So I'm evaluating it at that number. Repeat the same thing for z. Right, so that's my next point. Okay, so now I have 2 points. Yes, and they are, I guess, very close to each other. And as you change the value of t that you evaluate the y and z at, the points get further away from each other. So the next one, we go and evaluate at TP over 2. And then we do the same thing about z. So now the points are a little bit off. And keep going. Then it is going to be 3 TP over 4. Just make sure you don't make a mistake in inserting these formulas. Okay, so now you see the points are separated a little better. And now you go at full TP. And basically keep doing that until you get to, now after TP, you go at 3 TP over 2 and 2 TP. So this is going to be 3 TP over 2. And then it asks you to do it at 2 TP. And make sure you don't mess up Y and Z. And after 2 TP, now you go to 3 TP and 4 TP, and that's it. Okay, and finally, for TP. Okay, so you got your points. They're all defined. Very well. And now we need to basically connect them together. Okay. So first, it asks you to draw a line from origin to the first point and then connects the rest of the point together using a spline, okay? And then use the join command, connect them all together, rotate them, and so on. And it does that in generative shape design. So if you don't mind, and you see all of these points, instead of appearing under the tree, now they're all under what? This folder. So when I collapse it, I'm not going to see all of these 9 points on the tree. They're all inside this folder. So it is doing this part of it under generative shape design because that's where you can join entities, together and rotate them and so on. So what it is asking you to do is now click on the line command and then connect origin. And for the second point, you choose the first point here. Okay, so you could connect them together. Then connect the rest of these points using an spline. So then click on the 3D spline, and then you can go here, 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 and then keep going. Next one. Next one. Next one, and I guess there is one more. This one. And I okay that. Okay, so I got these two guys. Then I join that line and that spline together using the join command. Okay, and I join them. So now I have this join. And then this join, it is asking me to rotate it by that angle theta r and shift it. So I have to go and use the rotate command here. And it says what is the angle and what is the axis. So first I rotated about the axis perpendicular to the plane, so I use x-axis. And then for the angle, I use formula and say that is theta underscore r. Okay, and you see now it is rotated. Yes, you can clearly see that. I don't need the original one, so I'm gonna hide it. I need this new one, and I can hide all of these points too if I don't need them anymore. I just need this guy. Yes. Now I need to mirror that about the XZ plane. So I need to use the mirror command. Okay. And I want this guy to be mirrored about the XZ plane. What happened? Where is that? Didn't have any effect apparently. Rotate. Oh, not YZ plane, XZ plane. This one. There we go. Okay, so I got both of these now. Now I'm on page 13. And now these are the left and the right involutes, right? So these are basically this side of the involute and the other side of this involute and the other side involutes. So now what I need to do is to cut them at some point, connect them together using a straight line, and then the bottom of these teeth I need to use a fillet and basically do what we call actually that's a fillet, so nothing special. Sometimes there is an undercut, but here we don't do undercuts, so we just keep it as is. And now here it is asking you to create the outer diameter circle. Okay, so you use the circle command. Then you have to put it on the YZ plane. Then the center is going to be at origin. And it is asking you for a diameter. And for the diameter, I use formula again. And I use basically OD, outer diameter. Okay. And then here, all you want is a half circle. So you can just keep it as half circle. So here we go. That's this guy. Then I repeat that this time for the root circle, center it at origin. The support is going to be YZ plane. I make this one a full circle, and the diameter of that I make sure it is equal to RD. So this is going to be this one. There we go. And let's make sure everything is right because it doesn't look to me. I assume, let's see. Oh, it's radius, not diameter. So it should be RD divided by 2. Okay, and then this guy too. So radius, not diameter. So it's OD divided by 2. You have to be very careful. Now it looks correct to me. Okay, now I can see normal to this if I want to. Perfect. So now we want to basically go to the intersection, which is here, and we want to create a fillet. So we don't want this sharp connection at the root of the teeth. We want to create a fillet over there. Okay, so we use the fillet tool, and we can basically keep going from there. So if I expand the circle, I can use this corner tool, and my first element is this, my second element is that. Then it is asking for a radius. Okay, and here it is using clearance as the radius, so we go to edit formula and then type in clearance, and we do it, I guess on the wrong side. We have to choose which one. Let's make sure. Here it's gonna be this one. I want this guy. Okay, so make sure it is on the right side. Repeat this here. Make sure it is on this side. Again, make sure this is clearance. Okay, there we go. So we created this. Then we need a line, okay, to connect the end point of these curves together. So I use the line command and then connect this point to this point like that. Then I use my split tool to get rid of the extra stuff. So I go and click on the split tool, and then it is asking you to basically get rid of here. Let's see if I use this one as cutting element, and I can take away any part that I want. So I took the wrong side. Okay, so you have to be careful. I want this to be cut with that, and then I want that side to stay, the rest of it to go like this. I repeat that here. Cut with that, keep that side, get rid of the bottom. Then I assume that I have to get rid of the rest of the involutes on the top as well. So this time I'm gonna cut this with this one, and I'm gonna keep the bottom portion. Repeat that. There we go. Yes. Then we'll try to see if we can eliminate this part too. Okay. Let's keep this, and then let's see. There we go. So we did a bunch of trim and we cleaned it up a bunch. Yes. And now we have to go ahead and basically use this circle as my base circle to extrude, and then use that profile as my tooth profile to extrude as well. Okay, so what you want to do is in each one of these sketches, each one of them you do a separate, so I can select this and extrude it, then I can select those guys. Of course I have to join them first, right? So for example here, if I choose just this guy, can I just go ahead and extrude it? So if I go to mechanical design, part design, can I just extrude that? Yes. And then you of course have to provide some width of the gear. Now here it is just asking to go for 1 inches, so you can go 1 inch. And then as I said, you have to use that profile and basically use that for your teeth, right? So if I go back to generative shape design, I need just to make sure that I clean it up and it works fine, and join them before I can do anything else. So there we go. Now I have this profile and I need some stuff to join together to use as the profile of the tooth. And what you need is basically you have to get rid of these two as well. So let me get rid of them. This, keep the other side, go away. Let's see now. Okay. So now hopefully I have one profile. Let's just look at here. I assume it's good now. Need this, this one, this guy, and this one, and I joined them all into one profile. There we go. So now this, where's the join? I have to find it. So this join now, probably here, yes. This join I can use to create my tooth profile. Okay, so if I go to part design, I can extrude this 1 inch backwards, of course, and there we go. That's my first tooth. And then once I have one, I can use the circular pattern, and it says, what is it that you want to repeat? I want only that path 2. About what axis? Here about x-axis. And then how many of them? Of course, the number of instances. It has to be n. And then the angle between them is clearly going to be basically 360 divided by n, right? So if I go here, and if I say 360 degrees divided by n, okay, then I make sure I have 32 teeth. Yes, so this is a simple gear that I made. I can make it helical, but for the moment, I guess that's enough. I went all the way to the beginning of page 16. I don't need to go to helical right now. Just one last thing I want to show you is a hub and a keyway that is typical in gears. So if you know that, let's say the size of the shaft that you have in a gear is, let's say, 1.5 inches. Okay, so then you create the hole for that. Of course, you need to know the tolerance as well. And then you create a keyway, right? And I'll show you how to do a keyway. So use the line command and come down here straight, and then you go like that. Okay, you provide the right dimensions. You have to know the dimensions of the key, but if you know it, then you provide the right dimensions. So let's say 0.12, or let's say 0.2. How big is that going to be? That's nice. That's fine. And then you add the rest of the dimensions. So let's say this is 0.3. Then these gaps are each 0.15, and then use your trim tool and get rid of this portion. Get out, and then cut extrude the thing. Okay, so this is how a gear is. The shaft will go here, and then on the shaft there will be another keyway like this, and then they match each other, and then the key will come here and match them together. Okay, just as a final thing, let's just make it look nice, and we can finish it up. So here is your steel gear, Spur gear with the hub and keyway and everything. And you can, of course, convert it to a helical one later according to the last 2 pages of the tutorial. So hopefully that gave you enough of info about how difficult it is to make a gear properly and what parameters are involved in creating it. Thank you.